We've been going nuts about type affinity and storage classes. Let's try to understand the practical use case of where it might come and bite you. So here we have a table of type of name T1. It's going to have just one field with name A of type integer, and there's a unique constraint enforced on it. Let's now insert a couple of rows to see how things break. Here's our first insert. We're going to insert a value 0 enclosed within double quotes. 0 can be losslessly converted between an integer and a real value, so it's going to be stored as an integer here. Now here comes the fun part. Now when we try to store 0.0, this can also be losslessly converted into an integer, so a unique constraint violation is going to happen. So that's why it's important for you to store the right exact type of data that you declare during table creation. Either use a statically typed language or make sure that your library does all the essential checks before persisting data. Let's look at one more example. Here's another table T2. It has a single column of type text enforcing a unique index or a unique constraint. So when we insert the value 0, it's going to go through, and in fact 0 is now represented internally as a string. Select B comma type of B from T2 will show you that 0 is represented as a text, is stored as a text internally. Here's where the fun aspect comes into play. Now if you insert 0.0, based on our understanding, 0 can be typelessly without any loss be represented as 0.0. You would expect this to throw an error. However, since we mentioned the column type has text, 0.0 will be internally converted into a text before it is persisted. As a text, string 0 and 0.0 are not the same. So this one is also going to go through. So if you look at the select statement, both 0 and 0.0 are present. Again, bear in mind that we are looking at these examples to ensure that you maintain a strong check when you're interacting with your underlying database. Here's the last example for understanding the type affinity and storage types. So this is borrowed from the SQLite documentation section 3.4. Here they have created a dummy table T1 with a bunch of fields. Text indicates that there is text affinity. The next one has numeric affinity, integer affinity, real affinity, and blob affinity. And now we're going to perform a bunch of inserts. Let's see how things go through. The first one specifies a bunch of values. One thing to learn is, in case we don't specify the column names that we want as part of the insertion statement, then the order in which insert happens is the order in which the columns are defined in the create table statement. So T will be tied to 500.0, NU will be tied to the second one, I will be tied to the third one, and so on. Now once we execute this insert statement, the output of the select statement should now become apparent. We'll see why. So 500.0 is a text. The first one has text affinity, so it is stored as text. The next one has numeric affinity, and 500.0 is the same as 500, so it's stored as an integer. The third one is a real number, right? 500.0 again, and it can also be converted into a real without any loss of precision, so it's also stored as an integer. The next one is of type real. R is of type real, and we're trying to store 500.0. Well and good. It will be stored as a real underneath. And finally, we have a blob column. It has no affinity, so whatever you give will be stored as is. So here 500.0 is stored as text. So the next section here is used to demo the realization of a blob column. So we just remove the existing row, and now when we perform an insert again, you'll see that 500.0 will be converted into a text before being stored. 500.0, since the type is numeric and the conversion can be done losslessly between an integer and a float, the underlying type is an integer. The third one, 500.0, although it's a float, again it is stored as an integer because lossless conversion is possible. The next one is 500.0 tied to a real column affinity, so it's stored as real. And finally, in the case of a blob, since we gave 500.0, it's stored underneath as a real. Let's take up the third section of code. Here we are storing the following values. In the case of the first 500, it's converted as text, which is why we see text as the output. The next one has type affinity numeric. 500 is an integer, and well and good, it's stored as an integer. The third one, the type affinity and the data type match, the data provided matches, so it's stored as an integer. The fourth one, 500, is converted into a real number and then stored. And finally, for a blob, whatever the data's type affinity, the storage classes, it is used as is. So 500 is again stored as an integer here. The last two are pretty easy, but let's go through them. So here we are inserting a bunch of blobs, and no matter what the underlying affinity is, the storage class will always be a blob if you give a blob value. The same holds true for null. No matter what the underlying affinity is, null will always be represented as null under the hood.